Our next speaker will go on the same note. He will tell us how we can write greener code, but as well efficient code. Save the planet, save the energy. And so I'm sorry, I just seen he isn't wearing a... Yeah, okay, that's fine. So HDD, hey, scroll. Please welcome Bert.
So I'm not that good with computers, but this is actually true. There is a connector here. Good stuff. Yeah. No, this is good. Okay. Things are happening. Yeah. Not that much is happening. Usually this works. Yeah, my computer thinks it is talking to a projector.
Nee? Hij vindt nog van niet.
Try it again.
Pretty looks like it. So. Should we actually end today with the same issues that we started it with? Grab another adapter.
Otherwise, I have a solution for you. Otherwise,
you need a flip over.
Yeah. I have some lovely graphs that you cannot see otherwise. So
it's a Google Slides.
Yeah. Oh, we could do that.
As you shared with me, we grab your laptop.
Yeah, but then we still need to get it to your laptop somehow.
Yeah, we'll manage.
Oké, voorlopig is gaar. Okay.
Ja, deze proberen?
Ja. No.
Ga het proberen.
Usually this works.
Voorlopig is knippert heel erg.
Imagine how much energy we're wasting.
Actually, we're wasting my energy. So. Printers and beamers.
They both suck. It's not the converter.
No, it's not. The fun part is that we. Yeah, we had the same issue this morning. Erik.
Ja, als videokaart issue dan.
You know, I'm just going to start off.
Yeah, if you start off, we'll fix this. It's like teamwork.
Yeah,
well, we have to manage this like.
We're on difficult mode right now. So thank you very, very much for showing up. I know it's the end of the day. I know it's Friday. And I'm going to do another talk on energy efficient programming, energy efficient computing. And I want to thank the predecessing information because that means I can skip over a lot of stuff. And later I realized when I made this presentation that you are probably all very convinced already, in the sense that everyone wants to write efficient code. And we've been wanting to write efficient code for the past like 20 years, except now it's eco-friendly to do so. Whereas previously we just liked writing efficient code. And, but still, I think in this presentation I hope to give you a lot of interesting slides, which may help convince yourself that it's worthwhile to do it. But more importantly, it may also help to convince other people that are not yet as green-minded as we are. I'm mentally skipping to the second slide now. So who am I? What is my background? This is actually the good slide. Thank you so much. Yeah, did you sell my laptop or is it? Okay. Yeah. Okay. Thank you so much. So now we have picture. My background, I have done many weird things, but the most relevant background here is as PowerDNS, which is a maker of DNS servers. And those are used by KPN and Ziggo, Deutsche Telekom, British Telecom, and other places. And these process millions of queries per second. per provider. So that's a lot of stuff. And that really got me thinking a long time ago about energy efficiency. And it was in 2006. Who was born after 2006? Okay, it's not that bad. But still, so at one point, the AOL, which was a huge American internet provider, and they were suffering with a poor DNS performance. And at one point, they said, we tried all the name servers, we're going to now try Power DNS. And we worked very closely with them. And when we were done optimizing stuff, they could decommission 120 servers. And when they gave me that news, I was on holiday. And I thought, well, I've compensated my carbon now. But that still made me think a little bit that actually we do have an impact as computer programmers, because if we write inefficient code, we end up with whole data centers full of stuff. And so was sort of this planted in my mind that it actually means something. And other people had that idea before. And it may be hard to realize if you have a data center and you have 1 megawatt of computers in there, you also need to get that heat out of the building again, which also costs energy. And originally, data centers were not that big, and it didn't really matter that much. So there were many data centers that spent like 4 times as much energy on the data center than on the computers. So they spent like 4 megawatts maybe on cooling if they had data centers at that scale. And at some point, someone said, look, this is ridiculous. In America, electricity was nearly free. So no one really cared that much about efficiency. Like 10 times cheaper than it is here in Europe right now. So there were data centers that were just hideously inefficient, and over time the efficiency of the data centers has improved a lot. To the point that there are now data centers that say, well, we spend like 10% of the energy that goes into the servers on cooling, which is a very hard to believe number, by the way, but I think they are gaming the system. But anyhow, the data centers became a lot more efficient. But also, interestingly, until like 2000s, you had power supplies that would just sort of waste 40% of your energy, which is very hard to imagine right now. That you would take like, to get a megawatt of computing, that you would put like 400 kilowatts on fire just to heat the earth. And well, apparently that's what they did. That has now increased to 92% or even 94%. So the thing is, the hardware people delivered. The hardware people delivered whole factors of performance improvement, of energy savings, and sadly they have already delivered. So we cannot ask them to do that again. And so now it's our turn. But it does really matter, because every time a computer wastes a megawatt hour, yeah, we had to get that electricity from somewhere. When the sun is shining, okay, we can get it locally. In winter, we get that energy from terrible places, and like Norway. Well, and some other places. But it actually makes sense to sort of save energy. It actually really matters. The graph on the right, that's the CO2 rate of increase. This is not the amount of CO2 in the atmosphere. This is the rate at which that amount is increasing. And the rate at which it is increasing is increasing. This is not good. And we actually have a role in this. But do we have a large role in this? As has been argued, they say, well, the servers, they don't use that much electricity. It's like only 4% of all the CO2 that goes out, which means that the servers are operating at the same level as the aviation industry. So like all the airplanes of the world combined, which is a lot. It's also not that much, because everyone can say, well, our industry is only like 4%, which is okay. But if everyone says that, nothing happens. So we actually have some work to do here, because our 4%, yeah, we cannot complain about the private business flights and then we have wasteful servers. So now it's our turn to get to work, so get on it. Now, there has been a lot of attention to these physical data centers. People really hate them for some reason, but there's a lot of attention to the physical data center. There is no attention for what happens in the data center. So we say we have very efficient power supply, and the cooling is super efficient, and it's all super nice. And then inside there are all these servers running busy loops in NPM. It's not good. And the problem is, software has been getting slower, faster than hardware has been getting faster. And this observation has been true for the past 60 years. So Nikolaus Wirth, who died last year, was the inventor of many interesting programming languages. He built a whole operating system in his own special programming language, and he apologized that the whole desktop environment took up 2 megabytes. And it was a disgraceful amount of bytes. And like now we have fonts that are larger than that. Well, David Hay also said, yeah, the computers get faster. They double in speed every 18 months. Well, they no longer really do, but the software also halves in speed every 18 months. And abominations like React would not have been possible on hardware from the 1990s. So this brings me to this, and this will bring you to tears. It brings me to tears. If you want to waste a whole weekend on Wikipedia, read up on the Apollo guidance computer. This was the computer they used to land on the moon. It had 6,000 transistors, and it ran on 2 megahertz, not gigahertz. And actually, the 2 megahertz was also not really true. And this thing ran a whole operating system with priorities. That meant that it had a task called land on the moon. And it had also other tasks like calculate where the sun is and other stuff. And it would actually prioritize the stuff like land on the moon. If I would ask any of us right now, can you make a web service where HTTPS get life-saving information would always work, but sign up new customer would have lower priority than that? I would not know how to do that. I would not know how to devote the CPU to the get life-saving information part and making sure that it would not get overwhelmed by other URLs. Well, the Apollo guidance computer could do it. If you go to the Wikipedia, read on this, it will take you like a week. And you will cry, because it was so good. So this is one of my big claims. There is a factor of 100 performance between like crappy shit code, and then there is sort of middle of the road code, and we really worked on it. The distance between these two, I claim, is easily a factor of 100, and I hope to convince you of that in the coming slides. And if you would do that, let's say we would spend the time to really optimize our code, we could turn this data center into this data shed. This is a great ambition to have, I think. You could have one at home or in your office. And the thing is, the people were able to buy more efficient hardware. You can just order more efficient hardware, and it works just like the inefficient hardware. So people did that. Because it would also, they made their money back, because yeah, you buy the somewhat more expensive power supply, but it uses yet less electricity, so you make your money back. But if you want to make more efficient software, I cannot just shower money over it and that the software becomes faster. I must actually make time for it and build that faster software and give people permission to make the faster software. And it has proven to be hard. So I have the 3 categories of code. In category 1, everything has a spinner. So you click on something, the wheel comes, and then poof, there's an update. It's like super duper slow and dumb. And I have an example of this code coming up, which I wrote myself in Python, which I suck at, but in this case there was an asset. Then there's sort of the middle of the road code where you're like, hey, well, it's nice. I use it. People click on things, and you click on something, poof, the information appears. There's no time for us to draw a spinner. We don't have to draw a spinner. It's snappy. And the category 3 is sort of the most exciting part. That's like where you like every transistor is working. We have the whole machine is empowered, and it is filling up the pipes with data. And this is very exciting stuff. Now, this is an important thing that it took me a while to realize is if you have a computer system and you click on something and it takes a little while to get what you want. So you log in, spinner, after a while you're logged in. Under almost all circumstances, if you have to wait for something like this, there are several CPUs spinning at 100% rate. Because you could only be waiting on maybe latency. Okay, latency is free. Doesn't cost you money to wait a few milliseconds on a packet. Or you are waiting on a CPU. That means a sluggish environment is wasting huge amounts of energy. Maybe not in your place, maybe 3 data centers away, but anytime you have to wait a bit before something happens, the computer is not waiting, the computer is working during those few seconds. So it's not just a matter of, yeah, I'm not really happy how slow this system responds. No, I'm just burning up energy. And what I often see is that people build a system and when it's still small, so there are no users on it yet, it is already not snappy. And that is the moment where you would say, okay, we're going to take a few steps back because we are now relying on some kind of magical scaling later on. Well, it's not going to happen. So sluggish is bad. We already thought that, but now it's also eco-bad. So I have a small comparison here. And I have to first say, so this is the Dutch Parliament, tweedekamer.nl, that's on the right, and it's a profoundly sluggish site. I know this because if you are the first person to click on a parliamentary document, it takes 5 seconds to find it. And I don't know what it's doing during those 5 seconds. Is it writing the document? I don't know. There is very heavy caching on it, so not many people are the first one to click on a document. But I also run a Dutch parliamentary site called opentk.nl, which delivers the same service except with far more information density and stuff. And it gets documents earlier than the rest of the world. That means that I'm often the first person to actually click on a link, and then I have to wait for 5 seconds. I have to again say, these are the Tweede Kamer, Dutch Parliament, are very nice people. It's not their fault. Their architect, however. And how did I find that out? My system makes a copy of all Dutch parliamentary documents, which means that it can continue working when the official site is down. And I would frequently crash their backend, even though I would only download at most 1 document per second, which in my world is not fast. Well, it turns out that they have an architecture that if you download a 100 megabyte large document, they will retrieve that from a database, put it in several queues, and eventually it comes out again, and it would run out of memory. One person yesterday who I discussed it with had a theory that he probably also base64 encoded the document halfway through just to pass it in a URL or something. And that's the kind of sort of what I call the category 1 side. People have built an overly complicated architecture. Building a single HTML page costs 5 seconds. And my thing on the left is built by me, and the thing on the right is built by Capgemini, by a whole team. And they probably had to make it a bit complicated just to keep everyone busy. And so my site responds within 5.6 milliseconds if you search. It does tons of documents. By the way, at the beginning of the presentation that we missed, there was a QR code where you could get the whole presentation as a PDF, including additional links. That is repeated at the end. So there you could read all this bragging stuff. But the nice thing is, the site does 16 milliseconds latency on average. Sometimes we get mentioned in the press, and then we suddenly get 25 gigabytes of traffic, which is nice. And the latency continues to go down, because when we have more visitors, it all gets better. So 20 milliseconds, it's like really snappy. And it runs on this tiny server, which sits on my desk, which also runs my other websites. And I sometimes show this to people, and they're like, no, it cannot be true. And but I did a lot of work to make the site like super snappy. And then I like to tell people it actually runs on this desktop PC. At one point I caved because it only had 32 gigabytes of RAM. And that was not enough to fit the whole search engine index. So I felt really bad, but I spent €100 on getting the 64 gigabytes of RAM. And I gave the 32 gigabytes away to someone else, which was nice. But it turns out that so you can run this whole website, and it's quite popular. It's snappy. So I would like to call the Tweede Kamer, the parliamentary website, category 1. Everything is sluggish, and we put so many caches in front that you hopefully don't notice. And my site is sort of in category 2, where, okay, did some work, pretty snappy on simple hardware. Now, we need to measure this stuff. Does it actually matter in terms of energy usage, or is it just me bragging about how swift my site is? So I bought this thing, and it is a lovely machine. It costs €25, and I calibrated it. It is unreasonably accurate. If you can order it today, and it will arrive tomorrow. And it is a very seductive device. And you can pull it easily with the incredibly nice curl program. I don't know if Daniel is still here. But, it's really good stuff. And you can pull it every second and see, well, how much power is my thing using. You can connect it to anything. And below is a little bit of matplotlib and pandas to actually graph that stuff. And when you graph that, you find the following thing. This is my desktop PC, which is a rather beefy Lenovo Xeon computer. And it always uses 83 watts of power, even if you do nothing. It does not sink below that. It's very important to actually measure this stuff, because the vendor will say all kinds of things, but they are maybe only about the motherboard and not about the memory, which also apparently costs energy. You have to keep feeding those capacitors. So here I found I'm using 83 watts, whatever I'm doing. And if I stress out the computer a bit, it goes up to like 135. So this is really good. I was amazed by these numbers, but not as amazed as we will be a bit later on. So I made a histogram, and that means the computer uses 83 watts, even if it's doing nothing. Now, I'm not a big fan of cloud stuff. I really do not like. I like my bare metal. I like that stuff. But I've had to change my opinion a little bit, because I have these bare metal machines that are just burning 83 watts even when they do nothing. And I can program pretty efficiently, but it would be better if my machine was 100% busy all the time, which is what a cloud could deliver. So this was already something I wasn't that happy with to learn. Now we're actually going to calculate something. One of my side projects is the conversion of the Dutch administration of addresses and buildings, which is delivered. If you want to download that from the Dutch government, you get 83 gigabytes of XML. It's terrible to parse. It's really terrible to parse. And to help you a little bit, they also have a SQLite version, which they note does not actually have all the addresses. And this has technical reasons that are very fundamental, but it's a bit weird as a government to say, well, we have this official database of many addresses. You could be lucky. And at first I ignored that, but then I found out that an address where I actually worked was not in there. So that made it personal. So then I decided to convert our 83 gigabytes of XML into a straightforward CSV file. It's a nice service, and you can download that. And it's actually, I also have a free web service as a test, and there is a web shop in the Netherlands that uses my free web service. I would not do that, but I'm not stopping them. And here you can see some interesting things. The house numbers, there are 9.9 million addresses in the Netherlands. And here you can see that, for example, there are quite a few houses that have addresses that have house number 1000. It's a nice round number, probably picked by people who said, pick a big number. And you can also see peaks that 100 has a little peak, 200 has a little peak, 400 has a little peak. And also there are some people that went crazy with 10,000. And there's even one place that said, we can do 100,000. I don't know. But let's say you wanted to generate this graph. You have to go over all 9.9 million addresses and do a histogram of house numbers. And first, let's do that in a really stupid way. It's truly dumb. But I did not have to work hard for that because my Python skills are just terrible. So this opens up the CSV file and then reads all the 9.9 million lines and puts that all in a dictionary to count how often a number occurs. And it takes 12 seconds to do this, which is in a way impressive, because that's like 750,000 lines per second for the dumbest Python code I could manage. So well done. But still, it takes 12 seconds to do. Now, how much energy does it take? Now, we can measure that. On the left, you see these peaks, where suddenly my computer uses 105 watts of power. That's just the browser doing browser things. You don't know what it's doing. So after a while, I turned off the browser because my measurements weren't clean. So from 9 hours 41, I shut down the browser. And then I ran 10 runs of the super dump Python code, which uses like 132 watts. Okay, this is not the most useful way of looking at it. You can integrate the power use, and then you get the energy that is used. And to make this fun, I subtracted the basic 82 watts out of it to just get a clean signal. You can get a very clean signal. On the left, you can see my browser still doing its thing. And then it stopped, and I have very clean measurements. And so we spent more than 5 kilojoules even, for 10 runs, 520 joules per run. Okay, it's the baseline for like the really dumb code. Next up, This is just what normal people would do, at least the people I find normal. They would say, well, we have a SQLite database, and we're going to ask SQLite to add this up for us. And this works. I can do the trial 50 times. Measurements again. It's a bit messier, the data, but it's like 20 joules per run, which is sort of an increase, of a sort of improvement. It's like good stuff. And so that's the middle category, like what normal people would do if they thought about it a little bit. And then we have the extra special category where we say, now we're going to use some really powerful technology like DuckDB. Hello, Hannes. I mean, it's just, there is little in software that I love more than DuckDB. And so I also asked DuckDB to do it. And I'd be a little bit smart about this. I'm not going to restart DuckDB for every time I query it. I'm going to keep it live. And I actually had to do 1,000 runs now to get any decent CPU usage. And this is now 2.5 joules per run. Yeah, that's some impressive stuff. So summarizing, we went from 520 joules to 20 joules to 2.5. And the user would also be happier because the left solution with 12 seconds is definitely not snappy. The middle one, half a second, is like, okay, we can briefly show a spinner to you. And actually, it's pretty hard to measure how long DuckDB took. It's in the order of like 12 milliseconds per run. So we had 1,000 times speed up simply by thinking it through a little bit and using better technology. And my claim is that this is true for many pieces of software. And when people see this initial terrible Python code, they go like, yeah, but no one would do that, Bert. And I'm like, and I'm sure no one here in the audience would also do this, because we are at the Joy of Coding conference. We actually like doing this stuff. Most software is written by people for the joy of going home on time. They would not lie awake about this. They would like, hey, no, there are no errors, no warnings. Seems good. So let's keep it this way. But yeah, this one took 12 seconds. And the other one took milliseconds. So this is the code that is actually out there. Now, I want to tell you about this thing. And this is like, for the one, that red thing is an actual server. Not many people see these days, but this is what servers look like. And Netflix had an interesting philosophy. They were a very smart company at one point. They said, look, we're going to spend a lot of money on hardware. We can spend as much money as we want on engineering to make this more efficient. Because we scale to like 1 billion viewers, and it doesn't matter what we spend on improving the efficiency, it will always be worth it. So they started spending the big money on specific engineers also. They hired a number of very good engineers that did performance improvements in FreeBSD and in other places, which we all use now. So if you get a flame graph of some performance, that comes out of this work. And they made a server that uses 400 watts and can serve 45,000 streams at the same time. Well, that's like impressive stuff, which is less than 10 milliwatts per viewer. That means that your phone, which can use like 1 watt, could do 100 viewers. Well, that's just some super impressive stuff. And I show this just to say, look, this is out there. This is what modern hardware can do. Whereas if you ask a sort of big enterprise-y architecture environment, well, could you deliver 190 gigabits per second? No, it would take a whole data center. And the Netflix people can do it in 2U. So big up to them. And also big up for them for sharing all this. All the tracing infrastructure that you find in the Linux kernel derives from this, even though Netflix uses FreeBSD. It's hard to understand, but that's how it ended up. So my data shed is actually a possibility. If only we had the will to do it. If only people said, we're going to allow you the time to do the high efficiency code, and then we could get that factor 100 performance improvement. So the dream is sort of alive. Now, a few non-code things. Virtualization. It used to be that bare metal was like really more efficient than virtual hardware. People said it wasn't so, but Netflix is not running VMware on that red thing. I can tell you that. And if they did, it would like half the performance at the very least. These days, the good news is if you do simple things that are virtualized, there is really no power overhead. So this is 2 measurements of me compiling some stuff in the virtual machine and me compiling some stuff outside the virtual machine. It's the same. It's like, this is good. This did not used to be the case, even though the brochure said it. But never, it never happens that someone says, shall we compare the performance against bare metal hardware? Because you might as well say we're going to fire up our own coal-fired electricity plant. It's just no longer done, but it's still worth it. So this is like good news. This is because everything is virtualized now. But I also have some like really bad news. If you make it complicated enough, your virtual machine stack is not this efficient. And I know this from personal experience over at PowerDNS. We had one customer, they previously ran on 6 bare metal servers. And they were like normal servers, not too weird. And they got replaced by 1,000 virtual cores on the new everything virtual software-defined networking stuff. Every packet gets considered and recompiled. And so we turned our green solution of 6 servers into this honking stack of virtualization using 1,000 cores. It is worthwhile every once in a while to measure, am I still getting the sort of performance that I'm expecting? The client side. This is sort of interesting. And this is where my theory did not work. If you load a site right now and it's React or something similar, there is actually serious number crunching going on before the site does anything. And I thought, well, since people have 1 billion phones and we have these 1 billion desktop PCs, would it maybe be the case that if you add up all these users, your JavaScript needs like a nuclear power plant? It turns out this is not the case. LinkedIn is a very sluggish site, and I was barely able to measure it. This is 4 reloads of LinkedIn.com, so I got a lot of thought leadership. It's terrible stuff. But it turns out this is only 45 joules per load. And okay, so they have 1 billion users, so they say. And if you run some plausible numbers and you calculate it like, okay, you need 0.5 megawatt of JavaScript loading. And 0.5 megawatt is, of course, like a lot. But on a worldwide scale, it is not really a lot. Because there are gigawatt individual data centers, so we're not going to really fret it over 0.5 a megawatt. However, let's say the people over at React decide to sort of add a new feature which increases the power use of React by 10%. That probably adds up to a nuclear power plant worldwide. And that's something these people should think about. This is a stunner for me. So I was doing these LinkedIn measurements, and at one point my computer started using 45 watts more electricity. And I think, what's going on? Because 45 watts is like serious stuff. It turns out this happens the moment you load open.spotify.com, which apparently launches a worker thread in a busy loop. And I tried this a few times, and it always happens for me, and it probably happens for other people as well. And given the fact that they have like 500 million users, and yeah, of course, many of them are using it on their phone, but there are many corporate users that are using open.spotify.com. And if they're all using 45 watts, it sucks. It sucks like this. And I sometimes wonder, does anyone ever measure this kind of thing? Because the client is like, no, the client is not us. We do the data center, we have to pay for the data center, so we care a little bit about that, but we don't really care for the people at home. So, the cloud problem, I mentioned that one. So I'm like old. I come back, with PowerDNS, we originally had 3 servers, Tinky, Winky, Dipsy, Lala, and later we got Po. And if we didn't program efficiently, those servers would become overloaded, and we had to program more efficiently. It's like a real grandfather story. But we could not say, okay, just get 20 more servers. No, we had a natural limit on the efficiency of our code. And when we got more users, we had to program more efficiently. Whereas you can now easily find that you have a birthday calendar online and that somehow it's consuming 1,000 cores over at Amazon. This kind of stuff happens. So I worry a bit about that. So apparently I have 20 seconds left. I'm not sure if it's not true. Oh. Okay, I'll use a little bit more time. Okay. So I have a few suggestions. again, I mentioned this before, but if you start a project and it's already slow, it's not going to get faster. And people have some kinds of magical hopes that they say, okay, yeah, this software runs on a stack, which runs on a stack, which is virtual and is also virtual. And then we apparently hope that one day it will become efficient. And that day is not going to happen. The moment to turn back is at the very beginning. We're like, I need to understand why we are showing a spinner when we have 5 users enrolled to the system. What is going on here? And actually, at the very beginning, everything needs to be like, boom. And if it's not, figure out why. And I've also long hoped that when you use a complicated framework that is sort of not very swift, then we'll think, well, maybe it will scale. And well, there is a way of scaling where you say this system scales very well because it's already slow with 5 users, and it's still slow with 100,000 users. But I have lost all hope. So if I'm involved with any kind of project, I say, well, look, figure out why it is slow already, because it's not going to be easier later on. And again, why is this important? If that system shows you this spinner, somewhere a CPU is at 100%. It may not be your CPU, but somewhere it is happening. And figure it out. This is a specific one if you make some kind of project that people have the site open all day long, which is often the case if you have a dashboard or if you are Spotify or if you are whatever, just for fun. Buy this power meter and figure out what is my site doing on common hardware. Because if your site on a phone, people briefly are on the app and then they are off again, maybe, unless it's maybe Facebook, I don't know. But if you are providing a healthcare system that people are using all day long, it may well be that you are putting 45 watts on fire. This may also be, I know some of you are from the more corporate world, I'm not, but you could have a big green energy claim here. We say we save like 40 megawatt hours of transmissions by removing this weird bit of JavaScript. Also, I did a little bit of investigation. Where does all this JavaScript busy looping come from? A lot of it is advertising. Yeah, no one could have seen that one coming. But it is very interesting to do an audit on your website or on your service and see, look, what kind of crap is in there. And maybe some of it is launching a worker thread and is busy looping just to get that advertisement in 1 millisecond earlier. I haven't figured out what Spotify is doing, what that thread actually becomes. I'm sort of interested now. Is it Bitcoin mining? I don't know. Probably not. But it would be interesting to find out. So this is, again, some advice maybe. So we have the really dumb solutions. And the really dumb solutions are often not under your control because it's an API call that someone else wrote, it's still there. But it's very worthwhile to just audit your code and say, look, what are the things that are taking a second and eliminating those. And that's moving your project from it needs a nuclear power plant to it needs a single wind turbine mode. This is actually sort of, there are often quick wins available. If you just start looking, like for example, for my own computer, I found out that the big energy waste was my use of Spotify, which is very easy to address. And you will often find in your own code that there are also things that are quite easy to address. The more you move to the right in this graph, because eventually your software is so efficient that it can run on a tiny solar panel. That is extremely hard work. So in my example, I could lean on DuckDB to do the smart thing because some extremely smart people have made that so efficient. So the only thing I had to do was to decide to use DuckDB. That's not that hard a decision to make. But you might also one day be tempted to say, hey, I'm going to write such extremely efficient code. So we're no longer going to use a database. We're going to handcraft a special database that's like super efficient. And I can really recommend that you not do that. These super efficient projects, and there are more of them around than you think. For example, when you watch a video and it needs to be transcoded, there are people that have spent like months of their life in a dark basement optimizing the transcoding speed of FFmpeg. And these are very scary people. And it's very worthwhile to leave the work to them. And there are also compression libraries that are like this, encryption libraries that are like that. And these people are like very special, and leave it to them. Unless you are one of those people. But then it's your new life. Then you go like, okay, from now on, I am up to date with which AMD stepping number the behavior of the cache line changes. And again, you could be one of those professionals or use the work of one of those professionals, but do choose. So I would generally recommend trying to move your code from the left a bit more to the middle, because there the gains are like super. And that's probably already enough in many cases. There are whole factors of 10 you can get simply by looking at it. Except that no one does that stuff anymore, because it sort of ends up as a bigger cloud bill if you don't do this. And in many cases, no one in the company knows which parts of the cloud bill correspond to which project anyhow. So everyone can say, yeah, that wasn't me. I mean, we're not writing that crap. So there is not a lot of incentive to do this unless you tell people this is part of our green strategy. At which point you might get time for it, because yeah, people have goals. Yeah. We had an interesting talk yesterday at the pre-party that people are stuffing AI into literally everything. And I'm well aware that you could do useful things with AI. I'm actually somewhat optimistic that eventually we will find some useful things to do with AI. No, I mean that. But don't do it because everyone is doing it. Don't set the world on fire. So on the right, there is the data center from Elon Musk, which powers XAI. And he couldn't get enough electricity there, which is a big problem. So all these things you see there standing outside are gas-powered electricity generators. And they are running there, and they're totally illegal. He has no permit for that. But he's like, no, the AI must grow. And I urge everyone to really think that, well, do we really need that stuff? Because I did a brief test with how much power my computer uses when the GPU is active, and wow. I had to make a really broad histogram for that. So do give this a think. Do we really want this? And even if you use the ChatGPT AI, maybe you feel like you are not burning the energy, but you are burning the energy, it's just somewhere else. Dus I want to really urge you to leave it off with the 7 fingers. Even though I think they fixed that, but it probably required another gigawatt to get rid of the excess fingers. Yeah, I mentioned this one. Every company is currently struggling with this, with unexpectedly high cloud bills, and people are like, well, and then sometimes a so-called business decision gets made, where people say, well, we know we are spending like 10,000 euros a week on this cloud thing, but hey, business is good. And actually working on this is probably more expensive. And turning things off is also, as we heard in the previous talk, turning things off is also really scary. But if you turn your huge cloud bill into say, look, we have a huge CO2 footprint, it might be worth it to then finally figure out what this all is. Because maybe if you as an individual engineer also think, well, I'm wasting a lot of euros, like, well, they weren't my euros anyhow, but you might feel more incentivized if it's about the eco-friendliness. So my final suggestion, this is for your employers, give everyone a power meter. Just as a Christmas gift or whatever, it's 25 euros. And tell people, look, go measure your stuff at home and measure our software for fun. It is so easy to do. And in one day, I found the 45 watts. So it says 25, but it really is 45. You saw the graph. But I also found out that even when I turn off my computer, which I did not do often enough, it still uses 8 watts of power. Yeah, I don't know what it's doing, but it's still sitting there waiting to wake up, I think. But even the 8 watts. So now I'm sort of, because I'm Dutch, so now I actually unplug the computer. Which this thing can also do. That's a nice thing. This thing can also really turn off your computer. And then I use the Spotify app on my computer instead of in the browser. It still uses 5 watts. And since you use that all day long, it does. I mean, I use it all day long. So now I have my phone, which plays over the Bluetooth speaker. At least my phone is energy efficient. But really, give everyone one of these. It will probably earn itself back in a week. So, and with that, I'm rounding off. Good luck. We have we can only solve 4% of the world's energy use. If we work real hard, we can maybe reduce that to like 2%, which is nice. But really is our turn now. Because the data center, the hardware people, they did their thing. And now we need to do our thing. And good luck with that. And with that, thank you so much for your attention.
Are there any questions? I think we can do 1, 2.
What efficiency gains we use just to create bigger AI models and better weather forecasts, etc., and also reduce actual energy use?
Yeah, that would be true if you had a fixed pile of servers, but right now people are just building whole new data centers all the time. And let's say we would all be more energy efficient, the rate of new data center creation would definitely slow down. But you can always, of course, say, look, the business people are going to mess this up anyhow. Maybe that's true. But if we want them to do the right thing, it will have to start with us. Because otherwise nothing will happen. So, yeah, maybe they'll mess it up, but I hope that they won't. Yeah, maybe. But if we first clean up the 45 watts, I mean, I'm not going to listen to more music if we say 45 watts on the Spotify client. But again, this is a very defeatist thing. Engineering people will be like, hey, I can make my stuff more efficient. I should make it more efficient. And then hopefully other people won't do bad stuff with that. Well, the nice thing, the phone actually does that in like half a watt, or probably less than that. That's very impressive.
Well, you were using actual power management, which is awesome. But like, if you're in a work environment, for example, you are in a cloud environment, what would be a good way to measure to minimize your output anyway?
The bill.
Yeah, like that's kind of proxy, I guess.
Yeah, it's interesting. You would find that the Amazon, for example, people are quite good at compliance. So it might well be that you could ask them. And they would probably deliver that, because that's the kind of stunt that they do. So I would very much recommend figuring that out. And otherwise, just drive down the bill, because that will make everyone happy. And is a proxy.
Last one.
Is it an idea to have some green measurement of the website online?
Yeah, so from the back end or the front end?
Front end. So what you did with the Spotify, because you could do it with any.
Yeah. Now, I think it would be very worthwhile if we measured this for a ton of things. Because this is the very low-hanging... I found this out accidentally. So yeah, it would be very good if not only the site operators did that, but if also... that's why I told you to just get one of these, because you will probably find lots of stuff. And then we should... I think if I will tell the Spotify people, because I know a few of them, and say, hey, could you take a look at this? And I'm pretty sure that they will take a look at it. So yeah, by all means, buy one of these machines and report and complain. Okay.
Bert, thank you very much for your very inspiring talk. Enjoy.